Hello, I'm Eric Necessian. I'll be presenting some research on looking at middle school students learning binary counting using virtual reality. Other authors on this paper are Dr. Margarita Vinikov, Jessica Ross Necessian, Adam Sprzinski, and Dr. Michael Lee. We're all from the Department of Informatics at New Jersey Institute of Technology in Newark, New Jersey. So we're examining alternative tools such as educational technologies and how they could be used in STEM education, in this case, computer science education. And we consider these to be useful because instructors can vary in experience, teaching methods, and domain knowledge. So educational technology can give students a more consistent learning medium, but using educational technology, you have to be aware of that instructors can act as gatekeepers whether they choose to use educational technology in their classroom. So, following a participatory design allows instructors to be involved in this design process of educational technology and can increase their awareness and interest in using technology in their classroom. So for this study, we built a virtual reality educational experience to teach binary counting, and we tested on middle school computer science students that were at a summer camp, pictured below. The research questions that we were interested in looking at is, could a virtual learning environment impact user performance? Is it as effective as in-person instruction? And can learning in a virtual environment be engaging for students, can give them a positive experience? So before creating this piece of software and testing it, we looked at game-based learning, which are educational approaches to using games to enhance learning. Games-based learning studies have shown that mathematics learning can help improve the student's self-efficacy, motivation, and achievement. Ku investigated games-based learning on its impact with different levels of ability groups in mathematics. So both the high and the low groups improved in performance when using games-based learning, but only the low ability students actually have improved confidence through games-based learning only. So these findings helped direct our design of this virtuality learning experience called Cspresso. A virtuality experience user, causing them to be less aware of their physical surroundings, which may increase their confidence as they're performing math equations in front of their peers. So we're looking at how these low ability students can improve their confidence by removing that kind of self-awareness or that social humiliation when they're performing mathematics in front of fellow students. So games-based learning also shows promise in computer science education in K to 12 levels. So some studies that compared games-based learning and non-games-based learning versions of identical educational material demonstrated better results for games-based learning. It actually isolated out game mechanics as a factor that had the impact on learning. So researchers have also explored games-based learning for computational thinking skills, and saw positive results on engagement. And this also had a successful integration of virtual reality as a visualization tool in this experiment. So Winthrop made a case for a novel approach to designing games-based learning for computational thinking. He rooted it in constructionism learning theory, and that supported multiple play styles for how a student wished to approach the learning of computational thinking with their own preference. So our learning experience, Espresso, was designed around this idea of open exploration. We had a big open space. We had a lot of interactive elements that you could tinker with back and forth, but it wouldn't set the executable until the player was ready. So the experience was designed to account for multiple play styles by having all these interactables, these multiple actions stacked together, and then when the student thinks that the final answer is correct, will they actually execute on their decision? But at any point while they're interacting with the different parameters and the different parts of learning this binary counting, they can change parts of their answer and learn how it comes together. So for our experiment, we wish to examine if virtual learning environments have the same benefits of live instruction. In this case, for teaching a fundamental computer science topic of binary counting or binary math. We had 34 participants coming from this computer science summer camp. 19 were girls, 15 boys, and this was a middle school age range from 5th to 8th grade. We randomly assigned the participants into a control group, which had live instructor, and a treatment group, which had the virtual reality experience. On the left-hand side, you can see some participants in the virtual reality group being fitted with the equipment and actually engaging with the learning experience. On the right-hand side, you can see what this virtual experience looked like. This is like the finished, the refined version in graphics. But you see that we have these different stations that the user will be pulling levers on that changes the different states of these binary numbers. We have this fun narrator. In this case, it's this egg-type creature. And the whole environment in general is supposed to be just very bright and fun for children to learn this computer science topic. So this is what one of the learning tasks in the virtual environment looks like through the virtual reality headset. In this case, you see that the participant is moving their virtual hands through the virtual space and is pulling these levers. This is one station. This is kind of like the rough version of the number station, the first station that they interact with. And you can see there's 3 levers. So we have 3 binary numbers or bits in a row. And these are powers of 2, and you add them up. And so the participant, the student, is free to pull these levers back and forth and see how they change the sequence of numbers that get added up at the top in decimal format. So by playing with these bits, these levers back and forth, and seeing their translation to their decimal format and see them in the equation updated real time as they're interacting with it, and they have a legend on the right. We hope to see if this aids in their learning of binary counting. So this is a diagram, a top-down view of the play area. You see that there's these stations that are dispersed in a circle around the user. So the user gets spawned in the center of this virtual world. And this circle is a 10 foot in diameter, so it's like a 10 foot by 10 foot space that they need to move around in. That doesn't have any obstacles, there's no furniture in the way. But the user spawns in the middle, is then guided toward the task station, where they're allowed to then learn about and interact with these other 3 stations, where they can generate final output and bring it to the task station, hence completing one task or one loop. There's several tasks that are given to them that get increase in challenge, and this is what the virtual experience looked like in its finished high-resolution form. So you can see it's a big open space. It's circular in nature. The user is invited to move up to this task station to be given the task. It might be 3 red spheres or 4 blue cubes. In either case, they have to move to the number station to set the number of objects. Then they move to the shape station to set the number of the shape of the objects. The shape station was next because it's simpler than the color station, which you can see it on the left. We have a value lever for red, green, and blue, or 3 levers that mix together. And this was the hardest station because it's not a direct switching of numbers like the number station. It's a bit abstract, it's separated, it has to deal with knowledge transference because we're mixing numbers that are on or off, but underneath it's 3 bits that represent different things, and they get mixed together with their different states on and off. But eventually the user, when they're happy, they think that they can generate the output that's requested to them from the task. They'll go to the output station second to the left, and this output will be generated in this carrying cup that they'll bring to a task station, which will get told if they were correct or not. If they're incorrect, they'll get a hint and they'll have to go around the stations and generate new output. If they were correct, they move on to the next task, which is harder. And there's 7 tasks. So for these two groups, on the left-hand side, you see the instructor-led activity, the physical-based activity, and on the right-hand side, you see the virtual reality, what one of the stations looks like. So we had 2 groups, the physical group and the virtuality group, but they're all based on the same learning activity. So this comes from CS Unplugged. It's a very well-known website for teaching. It has a bunch of activities for teaching computer science or computational thinking concepts without actually having to use a computer. And we took the physical activity on the left-hand side directly as is from CS Unplugged, which is using these cards to flip up and down. So the little diagram image above the instructor, you can see that there's 4 cards, which represent the 4 bits, and the 2 on the right are flipped up, 1 and 2, and then the ones that represent 4 and 8 are flipped down or off or 0, and then you add them up for your total. And the same activity is reproduced in virtual reality. It's just the stations are separated out to give them some physical activity while they're learning this abstract concept. So the implementation of the experiment was we had the pre-assessment phase. We did our learning assessment. We trained the participants in how these activities are going to happen. The physical group went with the instructor. The virtuality group came to the gymnasium to get trained and fitted with the VR activity. In either case, they both had a 20-minute learning activity, and then they had their post-assessment learning assessment, and then the virtual reality group had a interview session to see what their usability and their feelings are in the virtual reality experience. So the learning assessment looked like this sheet of paper that they filled out with a pencil. This learning assessment came directly from CS Unplugged as well. The top part you can see is directly what the physical activity looked like, these flipping of cards to represent different bits on and off, and then how to know which power of 2 this bit corresponded to, and then how to add them up. The bottom part of the assessment you could see is asking very similar questions about a series of bits, but they're not using these cards that you can flip up and down. We're using different types of symbols to represent the bit on or off, and we're seeing if they can transfer that knowledge over to a more abstract system, just like we did in the virtual reality application with the colors. So we had a interview protocol to follow with the children. We did focus groups of 5 participants. So the groups that came into both the virtual reality group and the control group were groups of 5. And as the groups finished the virtual reality, one researcher took them to do a focus group interview. Based on interview techniques from Campbell, for small children, small adults, it's a better process to put them into focus groups where they're more comfortable talking to an adult, but smaller groups are better where they don't get a group think happening with a larger group of children. So some sample questions, we were looking more at usability. Questions like, how did you like moving around in this virtual space? Did you like moving and walking and pulling levers or doing physical activities while you were learning? Did you need to stop for any reason learning? Were you not having fun? Were you bored? Did you feel sick? Were you tired? Were there some type of negative effects that stopped you from completing the 7 tasks? And we followed a 3-stage coding process as subscribed by Campbell for inner coder reliability. So we had two researchers. We had a primary researcher read through all the responses from the codification. They generated this list of codes. And then the second researcher came through to review 10% of the responses and see if they could reach an 87% minimum reliability from the lead researcher. We did reach 91%. And so then the lead went through and coded the remaining open-ended responses and counted the occurrences. So what did we learn from this experiment? What were the results? So here we see the learning assessments, the pre and the post, and we found that there were no learning assessment differences between the conditions. So on the left-hand side, we're looking at the pre-assessments compared to the control group on the left and the VR group on the right. You can see that most of the participants coming in could not answer any of the questions on the learning assessments. We do have an outlier in the control group, which got one right, but the total of 14 questions, that's still very low. So this is discrete data. It's not normally distributed. These are unpaired groups. So we used Wilcoxian ranked sum test with a 1% alpha confidence. And when we looked at the pre-assessment on the left, we saw no difference between the control group and the VR group, meaning both group of participants had no knowledge of binary math or counting before going into either treatment. On the right-hand side, we see the post-assessment differences. So we see the control group on the left and the VR group on the right. We see that some learning has occurred. There is a difference from the pre to the post scores. But when we compare the two post scores of the groups, we see that there is no significance between the two, meaning they both learned just as much, whether it's live instruction or in a virtual learning environment. So this suggests that virtualization of this learning assignment and binary counting is just as effective in virtual reality or a virtual learning environment as it is to live lecture. And we move on to the interview data. As we codified it, we found a theme talking about user emotions. And within this user emotion theme, we have 5 codes with 36 total counts with all the interviews. And so we took the frequencies of these codes and we plotted them as histograms. On the histogram at the bottom, we have 3 positive emotions and 2 negative emotions. So 5 codes. 3 of them were the participants were talking positively about the experience of virtuality, and 2 of them they were talking negatively. So the 3 positive ones were enjoying immersion, or enjoying the idea of feeling that you are in a virtual environment. That was talked about 12 out of 36 times. We have participants saying they enjoyed the physical activity. They enjoyed walking and moving around the stations. They enjoyed pulling the levers. And that was 11 out of 36 times. And then the participants talking about just enjoying learning in general in this virtual reality application, 9 out of 36 times. So you can see the percentage of those reportings were all 33.3%, 30.5%, 25%. Very strongly reporting positive emotions compared to the negative emotions are of feeling bored or feeling distracted, both of which were reported 2 out of 36 times, or 5.6%. So since the positive emotions were reported so much higher than the negative emotions, we're going to suggest that the virtualization of this educational experience was indeed highly engaging and gave positive emotions to the users when learning about binary counting. So in conclusion, we presented binary counting to middle school students in a gamified and engaging manner. The students were observed verbally walking through the steps asked to them as they were physically doing it. They were also shown to be very happy and showing positive emotions like dancing around when they were successful in a task. And the VR treatment showed that learning binary counting can be done just as well in a virtual learning environment as to a live instruction. And this suggests that virtual learning environments can be successfully implemented as learning alternatives to help supplement traditional computer science teaching methods. Thank you.